Okay, so we'll start this unit with some information about a gentleman named J.J. Thomson. So those of you who've taken chemistry, this first little bit will be familiar, because really what this first half of this unit about is models of the atom. We covered models of light and how that model changed over time, and now in atomic physics we're going to look at first models of the atom and how that changed over time, and then we're going to move into nuclear physics, basically. So just a little bit of background before we actually talk about Dalton. In about 1810, John Dalton kind of put forth the theory of the atom that became known as the billiard ball theory. So his is the billiard ball. And what that billiard ball theory said, and why it was called a billiard ball, is because basically Dalton said that all matter consists of small, indivisible, indestructible particles called atoms. Okay, and I've already got a billiard ball written here, billiard ball model, and that there are no internal or external features in those atoms. Hence a billiard ball, right? It's round on the outside. There's no external features. You can't really break it apart, and if you do, there's nothing really inside it that's of any use. So that's his atomic theory. That's about 1810. He said that all atoms of a given element are the same, that each element's atomic mass is unique, that atoms combine together to form compounds, that atoms are rearranged during a chemical reaction, they're neither created nor destroyed. He didn't have, this is a thing here that kind of illustrates that there's a limitation to Dalton's atomic theory, is that although he said that atoms combine together to form compounds, he had no explanation as to why that happens. Okay, and that suggests that there is indeed an internal structure for the atom, which contradicts this part here, which contradicts the fact that Dalton said there was no internal or external features. So this is a contradiction here, and therefore it's a limitation to the theory. Writing with the mouse is really fun. Okay, that's good. Okay, contradiction. Limitation is maybe the better word for that. And I'm going to have to not write so much with the mouse. Anyway, this is an experiment to see if this works. Okay. So, we still use Dalton's atomic theory to explain things. Like, it was successful at explaining a number of chemical relationships. Law of conservation of matter, right? Law of definite composition, law of multiple proportions. So those are all still, those came out of Dalton's atomic theory, and we still use all those. So those are important. In about 1869, Mendeleev sort of carried on with some other scientists' work and continued putting elements into some sort of order that eventually became the periodic table. And so he put forth the properties of elements formed repeating patterns, and he put these elements in the same group, or the same column of the periodic table. So they have the same properties, things like chemical reactivity, boiling point, melting point. That here, again, just like the limitation of Dalton's model, it suggests that there's some sort of internal structure for the atom if we know that different atoms behave differently in different situations, and that there's some that have similar behaviors. That indicates that there's something going on inside those atoms that's the same to cause them to have those properties. And at the time that in 1869, there were 63 known elements, and the way that Mendeleev laid them out in the periodic table indicate like there were gaps. There were gaps where there were clearly some elements missing. So they're suggesting that there were some elements that were not yet discovered, and of course that's true. We have quite a few now, a number of man-made and a number of natural ones. Okay. So again, Mendeleev's, he had no explanation for the repeating properties, the repeating pattern. I'll just put for pattern. Okay, and then that brings us to these fun things called cathode ray tubes, which you saw basically a version of in class today with the charge to mass ratio apparatus, the Helmholtz coil that you use. So a cathode ray tube is a tube that is very close to being a vacuum, and it has two electrodes inside. And basically an old style TV, if you've got a TV with the big fat end on it as opposed to a flat screen, the picture tube is just a cathode ray tube. It's just basically formed from electrons. So with a high enough voltage between the electrodes in a cathode ray tube, it appeared that something was thrown off the cathode towards the positive electrode. So there's like a line, right? There's that green line of electrons. So the tube glowed when this happened. And so they became known as cathode rays because they came from the cathode and went towards the anode. So people called them cathode rays. And one thing that was found out is that the beam could be deflected by a magnetic field. And in about 1885, this was happening all through the 1800s, scientists were playing with these things. It was sort of like a new technology, a new apparatus they could play with, and they, there were a lot of scientists played with them for fun, but then there was a number of people who believed that they could actually come up with a better model of the atom, and they could actually figure out what was going on inside atoms by using these cathode ray tubes. So in 1885, William Crookes, he suggested that cathode rays were streams of negatively charged particles. Mainly to do with the fact that they, how they deflected in a magnetic field, and then also how they could be deflected by an electric field. And about 10 years later, in 1895, Jean-Baptiste Perrin, he showed that cathode rays will build up a negative charge in a metal cylinder, which sort of, these really indicated that those cathode rays were negative. Okay. Then along comes J.J. Thomson in about 1897, so just before the turn of the 20th century. He showed very clearly that cathode rays carried a negative charge. So this is an important part. This is the first step in his model, so that those cathode rays were negative. And he used discharge tubes with very low pressure, and he showed that cathode rays were deflected by an electric field. And so then that proved evidence for the existence of electrons. So basically, Thomson is credited with discovering the electron. That's sort of his big deal, his claim to fame. And a little bit more, too, which we'll talk about. So there, I'm just going to be short with the electron there. He basically determined that these things, the things that came off the cathode rays were all made of the same particle, so therefore they were electrons, or negative charges, which became known to be called electrons. He couldn't find the mass or the charge of the electron, but because he could determine the speed that the cathode rays were going, he could find the charge to mass ratio of the cathode rays, and that was really, really important. And that's basically what you guys did yesterday, was you simulated his experiment with a much more sophisticated device than what Thomson used. And so there's two parts to Thomson's process here, and we're going to work through it, and then we'll look at some examples. We'll also look at the conclusions that Thomson made given his experiments. So the first thing he did, and this is a diagram kind of basically of a cathode ray tube. Looks different than the one that you guys used yesterday, but it's essentially the same thing. Today. So the first thing he did was he would have an electric field and a magnetic field in the same device. So he used parallel plates to create a uniform electric field that pushed the charge upwards. So if we've got this stream of cathode rays, let me just see if I can change the color of the panel without changing the size. Because those cathode rays are green, right? Oh, well, there we go, I changed the size. Okay, so the cathode rays are green, and they would travel through here. Okay, so those are the cathode rays that have some sort of negative charge. Okay, I'll go back to blue and do that one. Okay, so he used parallel plates to create a uniform electric field that pushed the charge upwards. So if the charge is being pushed up by the electric field, so if we look at this, let's look at this, we've got, okay, I'll leave it thick because the writing actually looks a little better. So there's our electron. So we have an electric force pushing the electron up. Okay. That's an electric force pushing it up. So if that's the case, if this is a stream of negative particles, and the electric force pushes it up, right? So that electric force wants to push it up this way. Okay. Then that means that that plate has to be positive, which makes that plate negative, which means we have an electric field going down. Okay, so the direction of the electric field is down. And that's my electric field, so I call it that, my electric field. He then used two current-carrying coils, and that's sort of what this here is meant to represent. You guys had one coil in your apparatus. And those two current-carrying coils induced a magnetic field that pushed the charges down. Okay, so he has a magnetic field in there that made the charge go down. So the magnetic force acted down. So and like these curved arrows that I've drawn here is what would happen if that was the only field that was acting here. So if the electric field was the only field that was acting, then the electron would curve upwards towards the positive plate. If the magnetic field was the only field that existed in there, then it's going to curve down. Right? And if that magnetic field is curving down, using your third left-hand rule, right, your thumb points towards the right-hand side of the page, your palm points down because the electron is moving down, which means the magnetic field is going into the page, right? So my fingers point into the page. So if I draw some X's here, this is what represents then the magnetic field. The X is going into the page. I'm not going to do too many here, but this gives you the idea of what's going on. So that's the magnetic field going into the page. And so basically then what happened is if he adjusted the electric and magnetic field, it's not like the electric field didn't equal the magnetic field. That's not what happens there. He adjusted them until the electric force equaled the magnetic force. And then that meant that the cathode ray made it to the center of the end of the cathode ray tube, so it would hit here. So what that means then is those forces are balanced, right? So that means that Fe equals Fm. Okay. So if those forces are equal, and then the electron, or the cathode rays, sorry, because at the time he didn't know they were electrons, the cathode rays are traveling straight through to the other side, they're not balanced. And he could use that relationship to calculate the speed of the particles that were going through. So normally we would have, you know, F net equals Fm Fe plus Fm. This is our free body diagram that we have here, and if we have, we make down negative and up positive, okay, then we have 0 equals Fe plus negative Fm, okay, because our magnetic force would be negative because it's going down, which basically then means Fe equals Fm. And then going back to previous units and previous physics we've learned, we have formulas for Fe. So the formula for Fe is electric field times charge, and the formula for Fm is charge times velocity or speed times magnetic field. Like that. And the charges on each side cancel. Right, so the charge cancels because there's one on each side. And then he could, he would know the electric field strength and he knew the magnetic field strength. So then he could determine the velocity of those rays as they were traveling through the cathode ray tube by doing that speed is electric field divided by magnetic field. Okay, and that was pretty straightforward. And we've done this before, so this should generally seem like review, which means it was a good lesson to do as a recording. So if we just try an example to solve for this, this is pretty straightforward. A beam of electrons passes undeflected through a 2.65 Tesla magnetic field at right angles to a 57 kilonewton coulomb electric field. How fast are the electrons traveling? So we want to find velocity. Okay, we have a magnetic field. I'm going to dispense with the vector symbols at this point. 2.65 Teslas, which is actually a fairly strong magnetic field. And an electric field of 57 times 10 to the 3 for kilo. Okay, kilos times 10 to the 3. Newton coulombs. So we want to start with, if it's undeflected, then this means balanced, right? Like if you can draw a free body diagram that shows, although we don't know which whether the field is up, or which field is up, and which force is up and which force is down. But that's okay, we'll just assume the electric force is up and the magnetic force is down. So Fe equals Fm QE equals QdV. Right, and V will equal E over B. So 57 times 10 to the 3 Newton coulombs divided by 2.65 times, oh wait, there's no times. Sorry. I could try and use the eraser here. Okay. Teslas. Okay, and that will give us an answer of 21,509. Or with proper sigdigs, 2.2 times 10 to the 4 meters per second. Good. Doesn't let me pick. Okay. That doesn't need to be there. Okay. So, so that's what he did first with the balanced electric and magnetic fields. And basically what he did was he used just a magnetic field. So he turned off the electric field. Now that he knew the speed, right? So he'd find the speed. And then he would turn off the electric field and see, measure the radius of deflection, right? So measure how much this curve, right? Because there's a radius there in terms of the curvature from the center. And if he knew the speed and he knew the radius of curvature and he knew a few other things going in, then he could use the relationship here that Fm equals Fc, because now what you have, the better way of writing it is actually Fc equals Fm, because Fc is a net force. So let me actually just fix that because I want to show you what you actually have to show me here. So let's start with that one. So in terms of a free body diagram, the only force acting on this electron now, or sorry, on these cathode rays, is the magnetic force that's causing it to go down. And these turn off the electric force. So in this case, F net equals Fm. Right, and F net is just Fc. So we have mass times acceleration. Centripetal acceleration equals QEB. Centripetal acceleration, if we remember here, so let's say centripetal acceleration is v squared over r. So mv squared over r is equal to q v b. Okay. And we can cancel some stuff here. We can cancel a velocity on each side, so that velocity cancels, and one of these velocities cancel. And what he actually solved for here, what he got himself to, was the charge to mass ratio, so Q over m is what he was able to solve for. So Q over m, and that's going to equal V over BR. So what he needs to know here, he knows the velocity, he knows from this kind of calculation up here. He knows the magnetic field strength because he can control that, and he can find that out if he, the same way you guys did in the lab you guys did by controlling the voltage and knowing the current. And then he also knew the radius of deflection, and so he could find the charge to mass ratio of the electron this way. And he did do this. And so he made two main observations from these two different experiments, or these two different methods that he used. The first thing that he observed was that cathode ray particles from all cathode substances have the same charge to mass ratio. So he tried, again, what he did to try this with different substances is you fill the tube with different things. So maybe there's neon in there, there's radon, different gases, different elements in the tube, and that cathode ray, that stream of cathode rays is coming because basically you've got collisions happening between the atoms in the tube, and then the atoms that are coming off here, and that causes a stream of electrons to come out. So no matter what was in the tube, this number here always amounted to the same thing. So what he concluded from that, so this is his observation, and his conclusion from that is that the same particles come from every substance. Okay, so that was his first observation. So it meant that that stream of particles was the same thing, was the same particles for no matter what substance he used, no matter what element he used. And then his second observation, and this is kind of a bigger one here, is that the charge to mass ratio, this number here, is 1,800 times bigger than the charge to mass ratio for the hydrogen ion. So the charge to mass ratio he found from cathode rays, this is of cathode rays, was 1,800 times larger than the ratio for the hydrogen ion. And so if you're doing a charge to mass ratio and you've got mass on the bottom, and you're getting a number that's bigger than one that you've used before, then what that means is the mass of those cathode rays was much, much smaller than the mass of the hydrogen ion. So what was previously thought to be the smallest thing, right? From Dalton's billiard ball model, the hydrogen ion was thought to be the smallest atom. And so that was not the smallest thing, and that was not the case. So this means that the mass of cathode rays so cathode ray particles you know what, I'm actually going to try something different here that I think might work. Oops, this will just be a bit quicker. Of course this works. Okay, so the mass of cathode ray particles must be 1,800 times smaller. It's a big deal, they're smaller. Can I have it in here? Can I? Smaller than the mass of a hydrogen atom, which was thought to be the smallest thing. So the hydrogen atom was thought to be the smallest particle of matter, but Thomson discovered that there was indeed something smaller, something way, way smaller. Since cathode rays come from within the atom, This meant that something smaller than the atom had to exist. Okay, and so Thomson's model of the atom is called the raisin-bun model, it's called the raisin-bun model because there's negative electrons embedded in positive goo. Like a raisin bun. So we'll just do a couple examples here. And I actually think I'm going to try and write with text. We'll see how that goes instead of writing with the pen because it just seems a little bit easier. We have here, find the charge to mass ratio for an ion that travels in an arc of radius 0.35 centimeters. So the radius is 0.35 times 10 to the negative 2 meters. When it's moving with a velocity of 1.6 times 10 to the 6 meters per second, okay, and that's perpendicular to a magnetic field that is 2.0 Teslas. Tesla, my dream car. Anyway, that's a different story. Okay, so no, I don't want that big. There we go. Okay, so what we have here is we've got F net equals Fm, okay, which means mv squared over r equals QVB. Okay. And if we simplify this, right, because remember we can cancel a velocity. Well, if that's squared, it should be a squared up here, not down here. Okay, but then we're going to cancel it. I'll start another text. Okay, I'll go with the pen, because clearly I don't know what I'm doing. Okay, so that leaves us with mv over r equals qb. And then just to go over here, we have q over m equals v over br. And just if you're wondering about the algebra there, divide both sides by m. It's going to divide by m, divide by m. Right, so that cancels the m's there, and puts an m on the bottom here. So that b should be up here. So looking at that thinking, geez, that doesn't work. Yeah. And then divide both sides by b. Divide by b. Divide by b. Okay, so that dividing by b cancels that b out. And then so you have q over m is equal to v over br. So then that gives us 1.6 times 10 to the 6th meters per second divided by 2.0 Teslas times 0.35 times 10 to the negative 2 meters. okay, which will give you a charge to mass ratio of 2.3 times 10 to the 8 coulombs per kilogram, right? Charge over mass. And then sometimes what you might be asked to do is find, okay, what particle is this, right? Like, and the only ones you can use are electron. So charge of an electron divided by mass of an electron, charge of a proton divided by mass of a proton, charge of an alpha particle divided by mass of an alpha particle. Okay, so we'll just try an example from a slightly different point of view here. An electron is accelerated through a potential difference of 118 volts. It then enters an area perpendicular to a 0.63 Tesla magnetic field. What is the speed of the particles that enters the magnetic field? So if it is accelerated, so let's remember that basically what we have here is it's being accelerated. It's an electron. So if it's an electron, that means it originally starts at the negative plate, and then it's let go to the positive plate. And what that means is that this is electrical energy on the left-hand side, and that electrical energy is all converted to kinetic energy on the right-hand side. And so we have conservation of energy, which I believe is physics principle number 5. I don't know my formula sheet sitting in front of me, so, but I'm pretty sure it's 5. Momentum is 4, and energy is 5. So physics principle number 5. Okay, and so we have electrical energy equals kinetic energy, and this should have been the very first relationship that you started with in your lab yesterday. VQ equals 1/2 mv squared. Okay, so V will be equal to the square root of 2 times VQ over M. Okay, so we have, whoops, that went a long time. Okay, so we have 2 times the voltage, which is 118 volts, times the charge of the electron, 1.60 times 10 to the negative 19 coulombs, divided by the mass of the electron. Point 11 times 10 to the negative 31 kilograms. Okay, and that will give us the speed that the electron's going after it's been accelerated through this field, and that's 6.44 times 10 to the 6th meters per second. And what is the radius of the circular path it will follow? So again, whenever you're asked to find radius, you're always dealing with centripetal force, right? So FC equals M times AC, which is mv squared over R. So F net, because remember FC is just a net force, is equal to Fm. So we have mv squared over R equals QVB. And what we want to find here is R. Okay. So, we cancel. We're going to cancel the velocity. And to find R, R is going to equal mv over qb. And we use the velocity that we found up top there. So we have the mass of an electron, 9.11 times 10 to the negative 31 kilograms. Times 6.44 times 10 to the 6 meters per second, divided by 1.60 times 10 to the negative 19. This is a 10, not a 6. And that's negative 19, and that looks terrible. Coulombs times, what was our magnetic field strength? 0.063. test this. Okay. And that equals 5.82 times 10 to the negative 4 meters, a very, very small radius, which we would expect because an electron's a really, really small thing. So Thomson discovered the electron, and these are some of the calculations that he would have done to help do that. He didn't discover the charge of the electron, he didn't discover the mass of the electron, he discovered the charge to mass ratio of the electron. It was actually Millikan who used information from Thomson's experiment to then find the elementary charge. But that's the lesson. So I'll see you tomorrow for some to do some work on this.